everybody from Portsmouth and from outside. And we have the pleasure to have here from the University of Southampton, Dr. Matthew Partridge. So Matthew is a senior research fellow at the Optoelectronics Center in Southampton, and his main work is focused on application of fiber optics, sensing across different fields, from nuclear waste storage to medical diagnosis. And also you are very keen in outreach and in activities. For example, you've been involved in popular research focus blog that I encourage everybody to look at. And that is the Errand site. It's very well advertised there. So, Matthew, thank you so much for being here, and we are really looking forward for your talk.
Oh, thanks. Thank you very much. Yes, good evening. My name's Matthew Partridge, as Vincenzo very kindly introduced. And as he mentioned, I specialise in fibre optics. So I specialise in all kinds of different parts of fibre optics. I've worked in them for quite a long time. My career started out in science. I got an undergrad in biochemistry, which is a very long way away from optics. I did work in cancer diagnostics, developing reader systems, and sort of very, very slowly inched my way into optics, and then came back to academia, where I did a PhD in optical fibre sensors, and have carried on in academia ever since. It turns out that some of us really do quite like academia, and it is a really attractive place to stay working, even if you've had all of that very, very good pay in industry. It's quite nice to stay sometimes. And so I've been asked to come today to come and talk to you a little bit about fibre optics. And the remit I was given was to try and make this a broad and interesting talk about fibre optics, something that would be quite sort of widely appropriate to anyone who fancied coming to this lecture series. I did get given some inside knowledge that this is heavily attended by physics students who are encouraged to come. So I'm going to assume that a lot of you are going to find parts of my talk sort of like impossibly boring. But you'll be very pleased to hear that there are no equations today, and at no point do I really go into the actual physics of it. What I am hoping to get across to you today, and what I hope to share with everybody, is the sort of the more exciting side, the more interesting side of fibre optics, and particularly its history. Because from the history and the way fibre optics were developed, there's a lot of things that has been done with fibre optics. There's a lot of things that you can do with fibre optics beyond what I think everybody knows. So that's kind of the context of what I'm aiming for today. In sort of delivering this to you, as Vincenzo mentioned, not only am I a research scientist, I also do a lot of outreach work, and I run a science blog, and I'm a cartoonist, which is why almost all of the slides will take on a very non-formal look. So that first slide, pretty much the most formal font we're going to have all night. It's going to be mostly cartoons from here on out. They are a much more entertaining way of talking about a topic that's actually quite fun. So that also leads nicely into the whole, this is not a regular physics lecture, this is something that's hopefully going to be entertaining for you. So most people, when I come and do talks about fibre optics, even physics students, really just think about fibre optics as having one purpose. They do the internet. Essentially, they are the wizard that somewhere sits in between a computer and YouTube. And the fibre optics is just that bit in the middle that BT adverts continuously tell us does all the hard work. And obviously that is a huge component of fibre optics. Fibre optics, we wouldn't have the internet, we wouldn't be able to all surf YouTube during lectures and all the other things that I'm sure none of you are browsing right this second as I talk. But you need all of that. Most people, again, I hope that sort of the people who are more computer educated realise that it's not just one little bit in that network. Actually, sort of networks are made up of vast fibre optic networks. They're all interconnected with big backbones, huge trunk fibre optics, different types of fibre optics that go out to houses, fibre optics that can travel transatlantic, all sorts of different components of the fibre optic system. Which again is sort of, it's fascinating, but that is such a small part of what fibre optics are about. It's certainly where almost all fibre optics that are produced today go, comparatively, if you produce a kilometre of fibre optic, something like 98.9% of it will go into telecommunications. The remaining tiny bit goes to all sorts of other applications like the nuclear industry and medical diagnostics, which I'll talk about sort of throughout the lecture. But it's really telecommunications which is where it's taken over, and that's where we all know it from. But fibre optics, if you're going to take a long step back, obviously telecommunications is a really recent problem. And fibre optics have existed for longer than telecommunications have been something that, or computer connectivity has been something that we've needed. So just by, I'm going to do shows of hands. Who knows when the first fibre optic was first produced? Wow, that's the lowest number. Okay, there's one person. That person is now forbidden from putting their hand up for the next questions. So, by a sort of show of hands, who thinks we had sort of things that looked like fibre optics, kind of like early glass technology in sort of like the first 1,000 years? Who thinks it was something that came sort of within sort of like Roman civilization and things like that? Anybody, any takers for the Romans came up with it? Yeah, okay. Anybody who thinks it was sort of like a more sort of like 1500, 1600 sort of like beginnings of sort of fancy kind of glass? Oh, there's one taker for that. Anybody think it's in the last 100 years? Anybody think it's, within the sort of the 1900s? Oh, there's a lot more takers for that. Well, so there is a brilliant book which you can all go read called The City of Light, which details lots of the history of fibre optics, where a lot of this talk is from. The other place to do really good research on the history of fibre optics is obviously the internet. And if you ask the internet what the first fibre optic was, the internet will tell you that the Egyptians built them in tombs, and they had quartz rods to conduct light down into tombs. Unfortunately, if you look at these sites, the only reference to it is on the same sites that tell you aliens built the pyramids. If you actually look at a pyramid, there are no quartz rods in any of them. So it is very much a bizarre conspiracy theory that somehow the Egyptians built fibre optics that has somehow permeated the internet. The real answer is that the first evidence of fibre optics, the first sort of physics behind fibre optics, was really explored in the 1800s, the sort of the great era of invention, the great era of instrumentation. And it was in fact one of those brilliant inventions that happened twice at basically exactly the same time by two different people in two different countries. And it happened by Daniel Collatin and Jacques Babinet. One was French and one was Swiss, that this incredibly not racist cartoon portrays with baguette and Swiss Army knife. And they both discovered that they could do something that physicists and people, just generally didn't believe, that you could make light bend. Up until the 1800s, people understood the basics of light. They understood that you could put light through glass and prisms, and you could separate colours, do all these lovely things with light. But light travelled in straight lines. But what these two people discovered was that you could make the light that was going through the side of a barrel curve and go down into the pan of water underneath it, which is seemingly impossible. There was physics known at the time that they thought might be going on here, but this was something that wasn't meant to be realistic. This is not meant to be something that could have happened. And both of these people were sort of written up at the time as doing these demonstrations in big lecture theatres like this with a giant wooden barrel and showing off this essential piece of physics, where you had a light shining through the barrel. As this spout of water came out the side, the light reflected down the spout of water and into the pan underneath it, which had the appearance of curving the water. It had the appearance of taking the water and curving the light down with the water, which, amazingly, in that era, the thing that they were most excited about was that this packed lecture theatres. This was a real kind of crowd pleaser of a demo. And in the era of the 1800s, that was what you wanted. You wanted bums on seats, you wanted people paying to come and see your lectures. It was an amazing era because you got experimentalists doing ridiculously cool stuff with sort of explosions and glowing fluorescent lights and radioactive things. But this was something they really pushed for. And Jacques Babinet, he saw this and used it in a couple of his lectures, but Daniel Culloden was a sort of a showman. He was sort of like the ancient equivalent almost of Brian Cox. He liked touring with things that were dramatic and fascinating and interesting. And so this was something he thought, well, this I can get crowds with. And he wanted to try and kind of create as much as he could out of this and do things with it that would be things that would, again, attract crowds. And he was also quite a businessman. And so he was the first person to realise that you could turn this into something people would pay to come and see. So he used this reflection inside of light, not to do anything fancy like put it into glass or do other things. He found other applications for this in the theatre. So he had huge columns of light in theatre shows, which were essentially jets of water that were pumped with vast arc lamps to make it look scary. And the first one that he did was Faust, for anybody who enjoys the theatre knows a show all about the devil, and it had these huge red arc lamps shooting curved light all over the stage, and apparently it was quite a dramatic show for the 1800s. He was also commissioned to build a fountain. So in the World's Fair in the 1800s, there was this beautiful fountain that was lit inside by big arc lamps, and they were conducted, the light from the arc lamps was conducted through the jets, so it created this huge arcing curving fountain. There's a number of artists who do this now. Kew Gardens 2 years ago had a water installation based on similar things like this, used modern LEDs, not giant arc lamps. I suspect the reason for that might be that this was the 1800s before health and safety, and the first use of this bending light technology involved the death of at least 2 people. Because if anybody here knows anything about arc lamps, then these things in the middle here required operators. They were huge electrical arcing currents being used to generate lights before the light bulb. And they produced ozone and all sorts of noxious chemicals off the batteries. Obviously there was a lot of water around and it was incredibly dangerous. And at one of the World's Fair that was attended by the royalty at the time, the poor fountain people, 2 of them died during its use and had to be ferried out, and then because it was the Victorian era, new people were put in and the show carried on. That's how things happened. So it was not a great start to the introduction of the fact that we could do weird stuff with light, but it was at least something. Culloden wasn't the only person who looked at this sort of thing and thought this could have value, this could be something that could be useful more than just being necessarily pretty. And the next person who sort of like started to pick this up was a British man called William Wheeler. William Wheeler realised that it didn't have to be water, you could do it with other mediums. All you needed was a dense transparent medium and air. And using that difference in what's called refractive index, which I'm sure a vast majority of the audience actually understand what I mean when I say that, you can get this reflection. You can get the light bouncing through, in this case, in this pattern, glass rods. So William Wheeler's brilliant idea was to build a house where you had, again, it's before the light bulb, a giant arc generator in the basement. And that giant arc generator was producing your light, and then you would have glass rods running through your building, all ending in little mirrored reflectors in each room. And that would mean that you had light, you had the very first central lighting. You could actually turn lights on and off in rooms by removing little covers. This is, for a world that lived on oil lamps, this was a pretty revolutionary idea. Unfortunately for William Wheeler, and for anyone who can read really, really well on slides, this patent was filed and released, and he built his first test house in London the exact same year that the light bulb was invented. So, it's one of those technologies that was so close to making someone a lot of money, but sadly it didn't. So the house, I don't think it ever even worked as a model. There's not really any documented evidence of people going to it or anything. And it's pretty clear that you wouldn't, why have a giant arc generator and then tubes of glass running through houses which famously move and shift? It's just, slightly impractical, maybe more practical than an oil lamp, but slightly impractical. And so poor William Wheeler did not make his millions. I do think, because this, given that this was the Victorian era, I do think he did miss the opportunity, though, that he could have still found a practical application if he just combined it with the other great innovation at the time, obviously the beginning of Christmas. So, I mean, as great as the light bulbs were at the time, they were very large and required quite scary wiring. And I think he missed the calling of plugging it into a Christmas tree. I think that would have been a much, much better thing to be doing with it. Does anybody know what other applications people might have tried for this at the time? Yeah, your silence is matched to their silence in the past. Not really much else happened with it. It was really, you know, these fountains were produced, and this one house was produced by William Wheeler, and he messed around with a few other demonstrations. But in sort of like the end of the 1800s, there wasn't really much else being done with them yet. That was still slightly to come. But one of the biggest, I guess, drawbacks, and also you might realise a slight step difference between this being talked about as sort of fibre technology, where we're curving light around corners and bending it down rods and pipes, is that these are flipping huge. Fibres are tiny. So fibres, optical fibres that you know today and that carry all of our internet are minute. They are smaller than a human hair. They are very, very, very thin strands of glass. And they can do the exact same job that curved light was doing. They can do the sort of the same thing that the water was doing, and they can do the same thing that glass rods were doing in William Wheeler's house. But the important part that's kind of missing from it is that you need very, very, very small glass strands. And making very small glass strands is very hard. It's not something that's sort of practically, you know, easy to do. It's something that a vast amount of research has gone into since. And certainly for the 1800s, even though it was the era of instrument makers, that is something that is deeply challenging. The sort of the glass strands that were made at the time, anyone who knows anything about history of glass knows that making sort of spun fibres is very easy. So if you take glass fibre, or if you take a block of molten glass, and if you want to create very, very fine strands, you can make very short ones by just flicking this stuff. You can just sit there and flick glass. You can do it if you heat glass and pull it apart. You can make all these very, very thin glass fibre-y strands. And even in sort of the 1800s, they were doing that. So they were making sort of bales of glass fibre and things that were sort of like glass fibre made, sort of esque things for clothing and all sorts of other places. They were using these very, very short strands, but they were very brittle and they were completely uncontrolled, and they didn't have a way of making glass where you could make very consistent, very long strands, which is what you need if you're going to be doing stuff like projecting it around a house or across the Atlantic. Not that they had any concept of that. So what you have to do is you have to come up with a way of getting molten glass, essentially, to pull apart at a very consistent rate and in a way that produces a strand and cools at just the right weight. And conveniently, a man called Charles Vernon Boys put his mind to this, and for any of you that know any history of science in the 1800s, Charles Vernon Boys had quite a lot to do with quite a lot of fields. He was a brilliant man, and he solved the problem of how to make these fibres. And he did it in kind of, his paper on it, I would encourage you all to go and read, because it is a fascinating paper of its time, and I ache for the days when we used to write papers like this one. Because in it he describes not just his results, he actually describes his methods of slowly trying lots of different ideas that didn't work. And the paper is fascinating for it because it shows you all of his thinking behind it. So when he was trying to solve this problem, he had 18th century technology to do it with. Can anybody, I have two helpers at the front which will help with me in a moment, but can anybody guess how he went about trying to separate molten glass at a sort of a relatively constant acceleration, allowing it to cool in a strand-like formation? Can anybody have a guess how you could do that? Gravity? That's good. He found gravity too slow. So doing this sort of the shock drop methods and things like that, it just wasn't fast enough. Yep, another hand? I'm glad you said that, because that comes out almost every time, and I never thought of it when I wrote this talk. And every time I've gone and done it, people come up with horses. Oh, why didn't I think of horses? He didn't either. I don't know if horses would have worked, because his other methods were much faster than that. His methods went a lot faster than horses did. Anyone else? Sorry, clockwork. Clockwork, yeah, I guess, with very good gearing, he could have actually made that work. I'm not sure how much mechanical stuff he did. He certainly knew the right people for mechanical work. So the first thing he sort of tried, or he sort of gave up on, I'm going to ask my helper at the bottom here, Jessica, to give everyone a bit of a hint. So do you want to give everybody a hint of what he used? 1 second, technical problems. There we go. Ow. Thank you very much. So he wants to try a gun. So he thought if you put a blob of molten glass on the end of his gun, he would be able to accelerate the glass fast enough and sort of consistently as the ball came out the end of the gun, that he could create these strands. And he did spend some time designing a gun that could just about, I'm going to shoot the audience because I have to write a risk assessment. I'll go over there. And in his notes, he says that basically the thing that held him back was that while he could kind of design the rudimentary way the glass was going to be held and all this sort of stuff, he didn't know anybody who could make guns, so he couldn't go and explore that option. But at some point, he very nearly did try that. There was something else he tried before he eventually hit his final method. Anyone else? I will give this one to you. He wrote about trying rockets. He thought about the idea of setting off a rocket in his lab. In fact, he tried something else first. He put a blob of molten glass on gunpowder and lit the gunpowder. That was another way. He thought the explosion would separate the glass in such a way that it would form strands. It didn't. But then he wrote that he was going to try a rocket, and he did say that he just thought it might be a health and safety hazard to his lab, which I think if someone in the 1800s is saying it's a health and safety hazard, gives you some idea of probably how dangerous that idea was. And eventually he settled on his final, the thing that he actually did it with, and the thing that he solutioned. And again, I happily have Nathan to help me. So do you want to show everybody what he used? I get shots again. So if I can just steal that off you a second. Thank you very much. So Nathan has very kindly lent me this, which is a small Spider-Man crossbow, historically appropriate. But this is a very, very bastardized version of what he did. He built and he used a crossbow. So the very first fibre optic was shot by an arrow across the Cambridge quad from a crossbow built by Charles Vernon Boys. And his paper on the subject uses about half a paragraph to explain his fibre and about 5 paragraphs to explain the design and the beauty of his crossbow. He was a man that really loved his woodwork. And the design of the bolt that was to carry the optical fibre. And he spent a lot of time trying to come up with this. And they cracked it. He created a fibre that was around about 10 metres. Again, he doesn't just go into much detail about what he actually produced. But it's clear he produced a fibre that was about 10 metres. And he had a fibre that stretched across the lab. And in places, he said it was so thin that he couldn't see it. It was sort of probably in the order of possibly 10 microns or so. Which, given how he made it, is quite likely. And he thought this was fantastic. This was the first fibre optic. It probably wasn't very consistent across it, but it was an excellent way of it working. The interesting thing is that so far I've talked almost entirely about the light coupling abilities of fibre optics, because that was where that's the core unique selling point of fibre optics, is that they can get light from A to B round corners, essentially. And Charles Vernon Boys was an excellent scientist who worked in Cambridge, where one of the Culloden fountains was actually based for a short time. But at no point did Charles Vernon Boys put light into his fibre. There's no signs that at any time did he think, I wonder what will happen if I shine a bright light at one end and look at the other. And he didn't even consider it. The reason he made fibres was not for optics, it was for making incredibly fine balances. He wanted very, very thin, consistent glass fibres to act as sort of parts in holding up balance pieces. And that, you know, he did this amazing innovation for fibres and gave them, you know, their first sort of shot at being, you know, used in all these different kinds of applications. But unfortunately, that was where his involvement in it ended. And from there until the 1950s, there was all sorts of different activities in fibres. There was all these sort of different competing things that happened with them, all different applications that people found for fibres. Charles Vernon Boys may not have put light in them, but people in certainly the early 1900s did start to put light in them. And again, they didn't have computers, and while telecommunications was certainly very important in terms of sort of the war effort and everything else, no one was really thinking too much about how to use fibre optics for telecommunications. The things that they were excited for were things like dresses. So in the early 1900s, fashion, as it is everywhere, and in all history, very important. And one of the weirder parts in fashion history was the amount of animals, including birds, that people would use and attach to themselves in the name of fashion. And there was a huge craze for sort of things like having a dead hummingbird as an earring, or having dresses that were entirely made out of the feathers of rare endangered Papua New Guinea species. And when fibres first started being produced by people, and you know, hopefully, I think, you know, through all sorts of other methods and sort of gravity-fed crucible methods and stuff like this, the thing that people were excited about, and they were written up in newspapers as being a wonder technology to replace weird feathers with optical fibres. And so if you, I believe the exhibition is not on at the moment, but next time the V&A does an exhibition on the 1800s, you will certainly see glass dresses that don't look anywhere near as beautiful as these, which are modern equivalents, which were heralded at the time as the great kind of environmental saviours. We'll all be wearing glass in the next 10 years, kind of, you know, future thinking of fibre optics. And sadly, obviously, you know, we weren't all wearing glass by the 1930s, but it has become something that is starting to crop up in fashion and in art. And you may have sort of seen it now more in the newspapers, where fibre optics are finding an even more modern role in sort of smart clothing. So fibres can be used as sensors, which is something I'll get to in a little while, but you can have fibres that can detect heat, that can detect movement, that can detect pH, body chemicals, all sorts of things. And there are groups that are weaving fibres into clothing, not just because you can change the shape or colour of what's on them, but also because the clothing can then tell you something about yourself, or the bed can tell you something about the patient. So while this was a sort of a very exciting idea in the 1900s that never really went anywhere, 100 or so years later, we are finally getting around to doing something with fibres in clothing, and it is something that is being practically used. But even though this wasn't a big application then, what was quite a big application was dental work. So I would say the big drivers in the early 1900s for fibres was using fibre optics essentially as a tube for light, where you had a bright light outside the patient and you wanted the light somewhere near the walls. And having a kind of bent rod and then fibres that you could do it was brilliant. It really, really helped. And it was something that a lot of money was invested in producing and making. And it's still used, obviously that exact same technology is used now. It is realistically the same thing that was used then. That is probably the biggest commercial application, or the oldest commercial application of fibre optics, is essentially getting light into patients' mouths. Which is, again, not something most people think about fibre optics, and it's sort of an unusual thing that it would come from. But obviously the extension to this was that it's one thing to put light somewhere, but fibre optics have the advantage of the fact that they can take light from somewhere to you. And that was where the endoscope started to play quite an important role. So the first fibre optic endoscope came out in sort of the early 1900s, or the first half of the 1900s, I should say. And the first fibre optic endoscopes were revolutionary for looking inside the stomachs, taking images inside people's stomachs for the very first time, and images inside the parts lower down. And this was sort of groundbreaking and, you know, helped a huge number of people. I mean, an interesting fact about this is that the man who is photographed there, he was one of a particular group of people who was crucial to this development. He wasn't a scientist, but without him and people like him, the development of the endoscope would have been much, much harder. Does anybody know what makes him special? Exactly right. Give that man a free badge afterwards. This man is a sword swallower, and they recruited sword swallowers to help trial the endoscope because they were able to suppress their gag reflex and give feedback while they were having the endoscope. And they could tell doctors about what it felt like, where they thought it was, and all these sort of things. The doctors otherwise had no idea. So it's a great example of where sometimes in science we really need people who have nothing to do with our jobs to come and help us and give us insights. And you know, I can't remember how many sword swallowers were involved in this initial study, but I believe it was just, you know, in the low double figures. But it's one of the bizarre little quirks of history. But interestingly, I mean, the endoscope was applied to lots of different things in all sorts of different ways. When I sort of like prep for doing sort of this sort of talk, and when I've done this talk before, I always talk to my kids about what, you know, interesting problems I could try and solve with fibre optics, which is a bit something I'll do towards the end of the show. And one of the things they did come up with before was the idea of maybe using it for something more festive and using the endoscope to sneak peeks. It is worth saying that an endoscope, you can now buy like a toy endoscope for essentially doing like a spy kit for about £15, which is a long way to come. Neither of my children are ever getting bought one, no matter how helpful they are. But the problem, you know, the problem with fibres that they were making then was that all of these things had a sort of, they all relied on the same piece of physics, which was you had the glass and you had the air. And the glass and the air interface at the right angle created a mirror. And this is the total internal reflectance that keeps the light trapped inside the fibre. And in, you know, the initial fibres, they were just solid glass, and the light was in the whole piece of glass. And as it went down, provided you had air and glass, then it was fine. It would just go boing, 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 boing. If you got a piece of grit or a smudgy fingerprint, you no longer had a glass-air interface. You had a glass-burger grease interface. And burger grease doesn't have the same refractive index as air, and your total internal reflectance would stop. It wouldn't work anymore. So a lot of the rods, the fibres, and all the different things that were being produced had this problem of the fact that just light was falling out of them. You couldn't get light very far. That's kind of important for all of the future applications that you want to achieve with them. And very quickly, as people started to realise there might be applications in telecommunications with fibres, this was sort of recognised as one of the biggest problems. And trying to produce fibres that had all sorts of weird outside coatings that could prevent this or protect them from this became sort of the most important piece of science at the time. And sort of the way it is solved is you apply a coating so that when you put your greasy finger on the outside, it doesn't create any change in the refractive index difference. And so what you do is you put in a coating here with a lower refractive index, or a lower sort of optical density than you've got in the core, and the total internal reflectance is preserved. No matter what you put on the outside, it will stay the same. But again, doing this, a bit like making the fibres, is technically a very challenging thing. And just the idea of it, there's so many different ways you could do this. And in the mid-1900s, there were groups, there were companies, there was the post office, BT, all kinds of people had research groups that was working to try and solve this problem. And there were numerous different ways. Like there were things like coating it with rubber, coating it, having them immersed in liquids, in oils, in all sorts of things. But a few people started to play around the idea of something called a double-clad fibre, or clad fibre, which is where you have a core of glass and an outer layer of glass. And so to do that, you needed to produce two different refractive indexes of glass, two different optical densities of glass, and then produce a fibre that somehow had both of them, with one in the centre and one on the outside, without mixing. Which, isn't technically, it's challenging even now for people producing optical fibre, and it certainly was then when we didn't even have the faintest clue how to do it. And the thing that this needed at the time, and I think people knew that this might work as a brilliant solution, but they also knew that this was going to be a very expensive research project. And one person called Hicks found an unusual source of funding, or I suppose not unusual for the 1950s and 60s, in that he found funding from the CIA. So the CIA thought this fibre technology was interesting. They thought it was interesting for a lot of reasons, but the reason they funded him to the tune of several million was that he promised them he could make them a fibre optic encoder so that you could encode photographs using fibre optic bundles. Now, the way it worked was, it's sort of quite simple, really. It's quite clever, because how it essentially worked was that you had a big bundle of fibre optics, and you could have straight fibre optics, and whatever was in the image going in at the bottom would appear here exactly the same. It wouldn't change. But then if you had a load of fibre optics that was scrambled in a very particular way, so that that bit of the robot dog's forehead moved in a particular way, it could have a message encoded in it. Or you could have them all scrambled, take a picture of something, the film would just show a scrambled image. But if you knew how it was scrambled back in America, then you could de-scramble it. And what they were trying to come up with was essentially a way of being able to take photographs in Russia or whatever, and if the person is stopped or if they're intercepted, the Russians would have no idea what had been photographed. It would just look like noise. And then at the other end, should it make it to the other end, the CIA would have the other half and they would be able to reproduce this image. But to do this requires a lot of fibres closely packed together in a way that that sort of single glass core won't allow. And so this project brilliantly helped fund Hicks trying out the idea of using what's called the double crucible method, which is not particularly used now, where you have two regions of two molten glass, one drips through the other down the centre, and that produces these things where you have low index glass, high index glass, and the light is trapped within the high index glass. And that was the very first modern fibre optic that was produced as part of this project. And so you can thank the CIA for the designs. But the interesting part is this project has an interesting end, because you may have watched Cold War programs and stuff, and you may have seen James Bond, and at no point does anybody whip out a fibre optic scrambler, because these never made it to active duty. So the project had a fixed term date, and Hicks was well known to be sort of a bit of a workaholic, and he didn't really ever take holidays, but he did actually take a holiday at the end of this project. When he completed it and shipped the designs to the CIA, he went away on holiday. And in the first few days of this holiday, as on the beach, and as most of us will know, sometimes it's hard to stop trying to think about the thing in your lab that is annoying you to death. While he was on holiday, he wrote in his journal that he realised that as brilliant an idea as this is, actually, even with the computing process in the day, it's trivial to crack it. And once you've cracked it, it's broken forever. And he realised that the fundamental mathematics of the way the fibres would scramble the image are terrible. And the KGB will have cracked this in minutes. The CIA had, before he went on holiday, offered him quite a lot more money to continue developing this technology and continue creating better and better fibres. So just by a show of hands, who thinks he took the money and carried on with the research, and who thinks he turned around to the CIA and told them that everything he just handed in was complete rubbish? So who thinks he kept the money? Who thinks he gave it back? That's the closest to half we've ever had. You're clearly a good audience. He gave it back. He wrote to them while he was on holiday and told them that it was rubbish, and he gave the money back.
Oh, he didn't get the money, so he didn't really give it back. He said that it was never going to work, and he fessed up and he said that he'd found a flaw in the technology and that they shouldn't use it. And he then went on to found his own optics company, or part of one of the early optics companies. And it was kind of like it was one of those strange moments in history where someone did genuinely the right thing. And we don't all end up now sort of losing that part, or America doesn't lose that part, didn't lose that part of the Cold War just because of faulty fibre optic technology. But the fibres then, you know, we got fibres that were clad, we could get fibres that were long, we could get light from A to B. Great. So we've solved the bigger problems, the initial problems. Now you get onto the complicated problems. And the complicated problems are, again, they're sort of things that, you know, if you can't get light from A to B, you know, you don't really even think about these initially. But these are problems that does happen in telecommunications. So, and it was part of how we got the first telecommunication networks doing, you know, getting signals as far as they do. Because they realised that if you want to put in a digital signal, you've got on-off. You've essentially got these square wave pulses. If you send a square wave light pulse down a length of fibre, out the other end, you don't get a square wave. You get this spread wave of intensity of light where you get a bright bit of light and then it gets fades and it gets dark again and it gets bright again. And the reason for that is just because these fibres that they were producing had obviously many different optical parts. While they are very small, I mean they were in the order of sort of 100 micron or something, perhaps potentially at the time, 100 micron to light is massive. It's a fat thing. And light within that would happily go from one end to the other with a total internal reflectance down lots of these different paths. And these different paths are called modes. So you've got very, very, very long paths, very quick paths in purple, where if they're at a particularly sort of high angle or a shallow angle, they'll have their path down the fibre is obviously a lot shorter than if you send light down at high angle, where you've got a lot more length and a lot more reflections as it goes down. So light coming down different modes arrives at different times. So your ability to transmit information is really ruined by this what's called mode stretching. And trying to then solve this requires just initially making better fibres that are thinner and thinner and thinner. And now the first fibres that sort of started to look at solving this did it in a few different ways. I won't get into most of them, but the simplest one to explain is really they just made them thinner and thinner and thinner until eventually they could only propagate a single mode of light. And that's what a lot of sort of single mode fibre is known as. And that's single mode fibre was the thing that then became the default fibre for telecommunication networks. The first transatlantic fibres were sort of single mode based. And they were such that the only path that could be sustained was the central path, the sort of zeroth path, and it just went straight through the middle. So if you put in a higher angle, if you put in a high mode, it would couple out of fibre and it wouldn't be maintained down the fibre. And so in that way you could get a sharp pulse in at one end and a sharp pulse out the other end. And there's then a huge amount more to that, because the way that those have then been improved, and now we have multi-mode fibres where you can go back to this, but you can then demodulate, you can do things where you have shaped refractive index, all sorts of other crazy ways of solving this problem. But the simplest was really just trying to eliminate as many of these paths as possible. The other problem that they were having is that, it seems almost taken for granted that if you have a window pane, you can see through it. If you have a piece of glass, it's clear. Actually, that's something that has taken a lot of work. And I'm not going to kind of spend too much time on explaining it, because to be honest, this is a level of chemistry and technology that is something that I'm not that familiar with.
But around the sort of the mid 1900s and into the later 1900s, one of the things that really helped fibres was just making better and better glass with sort of lower and lower loss that was more reproducible, where they could make huge kilometre lengths of fibres that could transmit in ways that sort of wouldn't cause aberrations and other such issues. And the sort of point at which it got to the point where they could commercialise it was they built a few commercial systems using single mode fibres for sending signals across the ocean. By sort of the 1970s, there were a few different companies that were starting to produce it. And the very first commercially sold piece of fibre communications technology was sold to, not that particular person, but it was sold to the Dorset Police. It was sold to the Dorset Police because the Dorset Police were using, like a lot of police forces at the time, radio masts to communicate around their constabulary areas and then to their radio cars. And this was common practice all over the UK in the 1970s. And a radio tower in Bournemouth, which is not very far away from here, was struck by lightning and knocked out. And the constabulary in Dorset was so frustrated that this could happen, and they were sort of, that relatively, common occurrence of nature caused such a massive problem. They contacted the Central Police, who contacted the Home Office, who contacted the Special Sciences Department, and eventually it all got through to one of the first fibre optics companies who offered to supply them with the first fibre optic communications between radio towers to ensure that from the central station out to the outlying areas was always protected and didn't rely on a daisy chain of radio signals. And they installed it, and it immediately worked. And it worked very well. It worked better than had been spec'd. The signal was strong and it worked reliably, and it was an immediate commercial success for that company, who off that one test bed, started selling it all over the world. And it was off that one installation in Dorset, which again seems an unlikely place to have the first piece of fibre optic technology. It then grew and grew and grew and expanded into the huge network of communication that it is today. And in fact, the network of communication has pushed the technology so far. We want to be able to send signals so far around the world, across transatlantics. The record for the furthest piece of communication, the furthest signal ever sent in a piece of fibre optic is around about 150 million kilometres. I mean, you'd have to read the paper. There is a lot of fine print to this number. I mean, it's quite a beast of a paper that went out this declaration. So this is a slightly headliney, something in a newspaper figure. But essentially, they sent a signal 150 million kilometres in a piece of looped fibre to show that you could send a signal, a pulse signal, and then retrieve it after that. And that's sort of where we've got to with our technology. We can send light that far and still recover the signal. That's how powerful these are now. And again, to put it in context that's meaningful, because that's kind of an insane distance. I mean, it's very hard to understand how far 150 million kilometres is. Even if me saying from Earth to Sun or 250 loops around the moon is just stupidly big. But conveniently, the season has given me a brilliant time where I can relate this to something a lot more festive. It turns out, based on some maths this afternoon, and very hand-wavy maths, there are about 200 million children in the world, plus or minus some. And there are about 512 million square kilometres on the planet, which, if you quickly do some maths, works out at around about 2.6 kilometres per home, because it's sort of assumed for groups and stuff like this, which really, really conveniently means that there is, Santa needs to cover about 196 million kilometres, which is actually pretty close to the world record of 150 million kilometres that you can achieve with a single pulse of fibre. So this is sort of coming to the end of this bit.
interestingly, I've talked all the way through here about fibres that are solid, fibres that are made of glass. The fibres that are being produced now, the fibres that Southampton works on, the fibres of which Airguide is named, are actually air-filled fibres that have very, very clever geometries in the glass and the structures and the capillary structures and stuff. And we've managed to make fibres that don't have glass in the middle and the light is conducted down air cores. Which I think, if you're trying to persuade me that Santa can get down a chimney about that big, I reckon we can stretch. And if we have hollow core fibres, I think we could get Santa going to every home through fibre optics in the future. I think we've just modernised the myth. It doesn't seem impossible, apparently. So I think it's something that's evidently possible. So I'm going to stop here a little bit earlier than the hour, because I'm going to ask you guys to ask me some questions about fibre optics. And as the title of this talk sort of said, it's fibre optics can save the world. So there's so much from fibres. There's more than telecommunications. I hope I've kind of shown that in some of the historic stuff, where it's all come from. But there's even more to do with sense technology, to do with ignition of fusion plants, oil exploration, all kinds of stuff. I can't possibly cover all of them in a satisfactory way. So the method I've come up with is, you can ask me just a direct question, or if you give me a problem, a world crisis or a world problem, I will try and solve it for you right here, as I stand here, using some of the current fibre optic technology. So I will get Vincenzo to come around with the microphone, and I think we've got about 15-20 minutes of questions. Brilliant.
Yes, thank you so much. That isn't working, by the way.
Ah. So you can make fibre optic acoustic microphones. So while Vincenzo's fixing it, fibre optic acoustic microphones are used in marine research and oil exploration. So you can have very, very long fibres that they drag underneath the ocean, and they use to listen to oceanographic sounds being reflected around. And they use it for a variety of things, so for marine research, but also for leak detection in pipelines. They put microphones in the pipes and listen for where you get issues in the pipes. Acoustic fibre optics is probably, after telecommunications, one of the fastest growing commercial fields of fibres. So, convenient segue.
All right, thank you, Matthew. So, please.
In the printed introduction, it says, these wonderful cutting-edge devices can do amazing things and fix almost any problem. How about climate change?
That is a good one. So one of the things about fibres, and one of the things that was almost immediately very successful with fibres, this is going back a little bit as well, but was that copper communications take a lot of energy, or took a lot of energy. Switching to fibres has been a huge saving in the amount of energy it takes to communicate information across the world. That has already been quite a big saving. I think the thing that fibres are hoping to do, with more looking at environmental issues, is that they are very, very low energy for all the applications that they currently do. So where fibres are starting to replace things in sensor networks or telecommunications, they are always consuming less energy than the things that they are doing, which is more a sort of it's one of those, it's almost like a cop-out, because you're kind of saying, well, if you do our thing, it's clearly better than the old thing, so therefore it will fix everything. More directly, the fibre optics, the sort of the sensor side of things, so one thing that they're being used for is meteorological research, and actually studying the impact of the various things we are doing to the climate. And there is a plane research project out of the university called Cranfield, where they strap fibre optics onto the wings and fly it through clouds. And the idea is they're trying to understand the impact of particulates, the PM particulates, on clouds, in the hope that we can realise quite how badly we're doing. So I hope that answers your question. I hope it will definitely fix everything, and also it's helping to actually look at the issue and hopefully make it more of a current problem, a current thing we'll look at. So.
When I was your age, the big hope was optronics. But I think that all your optical signals in fibres now have to be converted back to electronics in order to do the switching. Whatever happened to optronics?
So there are optical switches, and there are optical transistors, those exist. You are right that essentially that technology was huge next week, and has forever been. Next week it will definitely be huge. The only thing I could say to it, which is I'm really happy that I read an article yesterday on quantum computing. So in quantum computing, there are many competing quantum computing technologies. And I was very pleased to read in the article that the one that seems to be winning for the fact that they can reproducibly build them and that they can make them at scale is photonic quantum computers, where the circuitry, the normal copper circuitry, is being replaced by photonic links because they work better for quantum computers than the copper does. And so, while I don't think we are going to replace my Apple Mac with an Apple Mac that glows, it is looking, and the current thinking is the next generation of computer technology, where you have got optical switches, it fits better with the quantum computing and qubit technology than it does with our original architecture of transistors and chips.
World hunger.
I see, that's a good one. So this is good because I worked on a project for about 6 months where the idea was, so fibre optics are mind-blowingly cheap. So if you make, it depends kind of on the cable, but a metre of fibre optic, depending on what you're buying, could be as little as a pence. You know, it could be incredibly cheap. It kind of has to be when you're reeling like 100 million kilometres of it around the Earth. And so one project I was involved in was using short lengths of fibre optics coupled to Raspberry Pis to measure the hydration soils and the soil moisture content, which in the UK, if you know the soil moisture content in a field, brilliant, you can get an extra 0.1% yield on a field. In the Philippines, where you're growing rice crops and trying to manage irrigation, you can make an 80 to 90% increase in yield in the food production in third world countries, because understanding the way that food is irrigated is incredibly important. And if you can make a sensor where your main sensing element costs a penny and the rest of it is powered by open source chipsets, then that goes a long way into improving food supplies in a sort of in a way that anybody can sort of download ideas and print them and run them. And there's a few different sort of water projects which do the same thing. They use fibres as water level indicators in wells and things like that. So I hope that's close enough. Thanks for a really small question. Yep.
You mentioned to me about fibre optics and cold fusion. How would fibre
cold fusion?
Not cold.
Oh my god. that doesn't exist.
Fusion.
Just fusion, yeah.
Normal fusion.
So there's several different fusion projects around the world doing various different things, but one of the fusion projects, I think it's in Europe, I believe it's in Germany, uses huge laser sources as ignition sources, and they do fusion, like point diffusions. They just do one hit, you get one fusion event, then you load it again and do another one, as opposed to something like the torus that runs continuously. And in those, they're trying, what they have to do is to create the fusion, you have to get a molecule, and you have to hit it with an insane amount of energy. You have to hit it with kind of like a sun's worth of energy. And the way of doing that is you have a huge number of lasers and you point them all at this same spot and you press go. The trouble with lasers is they tend to be quite large and often they're so powerful and so big they need to be stored 2 buildings away. And the way you get the light from those giant lasers to this single molecule sitting inside this large container is you use fibres. Now, interestingly, glass fibres have a limit, because oddly enough, if you start to put lots and lots and lots of energy into glass, the glass starts to get hot, and eventually those molecules just can't take the amount of energy you're trying to couple down them. And that's one of the big advantages of things like hollow core fibres, where you can couple light in a hollow structures, you can couple it into a vacuum, and they have incredibly high power limits. I mean, you can put gigawatts almost of power through those things, insane amounts of energy coupled into fibre optics. The hard part is making to get it in the first place, because if you miss by like a few nanometers, your fibre will explode. So some of we put kilowatts routinely into hollow core fibres, and the microscope images of them afterwards is often bits of broken and splayed molten glass. So it takes a lot of engineering. So yeah.
Removal of plastic pollution, particularly the microplastics.
So microplastics. So one of the things with microplastics and looking for them, and the PM particles as well as another similar thing, and looking for microbeads, is you can use microfluidics as particulate counters. So the UCL did a thing where they had 3D printed microfluidics, where you put on a little drop, and the drop went through your microfluidics, and it went past two fibres, one of which had a laser, and the other which had a camera. And as the liquid passed through, the particles interfere with the laser light that's being coupled between the two fibres, and you can count and size the particulates that are there. So you can easily pick up your little microfluidic, do a drop, say how bad your particulate problem is, and hopefully find out where more of them are coming from. I mean, I'd love to think of a world where we could actually get rid of them. The interesting thing about fibres is one application that's really nothing to do with their light properties is, I don't know however many people have ever had dialysis or have ever been on a machine that has cleaned their blood, but you can buy dialysis packs which are designed to filter blood samples, and those are packs about this big, and they are huge arrays of glass fibre tubes. And their job is to stop particles of certain sizes going through, and they are huge filter blocks for particulates. In the most common application for people who are in hospital, but I don't think it would be practical to filter the entire world's ocean through them. But maybe we can just test and find the bits that we need to.
So there is time for one or two questions.
I think there's one there. And then,
One there. So please go.
oh, do you want to go here?
Brexit.
You know, there's two questions that I get asked every time I've done this thing. It's either Trump or Brexit. Amazingly, I've had to go with answers that are politically neutral. I went to a conference a few years ago where I went to a toe curling talk where they presented a piece of fibre technology which sticks with me a lot, where, as I mentioned, it's used as medical sensors, because what you can do with the fibres is if you take them back to their original shape, their original style where they were quite leaky and the light would come out very easily. Well, if you coat your fibre with something like a protein, when it binds another protein, it can become more or less leaky to light, and you can measure that. And so you can use them as sensors for biologicals, for proteins, for neurotransmitters. And there was one group who had coated fibre optic sensor in neurotransmitter receptors. And they had discovered that what they could do is when they added a neurotransmitter, they could detect that that neurotransmitter had passed across the fibre optic. And the reason fibres were used, as opposed to one another diagnostic, is fibres are made of glass. Glass is quite inert. You can implant glass in test subjects, which is what they did. The test subjects were little mice, but that doesn't necessarily make it better. And they put the glass tubes into mice brains and watched neurotransmitters be released across these fibre optics using the change in fibre optic signal. They could detect the way that the neurotransmitters, their brains were functioning as they were running around. Now, how this solves Brexit, I brilliantly segue, is I think we all get along a lot better if we knew when people were telling the truth. And lie detectors don't work, but I'm willing to bet if we start sticking neuro detectors into politicians' brains every time they're on BBC Breakfast, they'll A, either start telling the truth more, or B, we could maybe detect when they're lying. And I think that would make the whole Brexit debate go a lot easier.
Very good. So this is the last question.
have a problem with plastics and disposal of same. What are your solutions to the disposal of fibre optics?
That is a very good question. So these are glass. These are things that are not going to naturally degrade. And fibre optics, glass fibre optics like this, are not something that is kind of easy to reclaim. They are things that when they are buried in the ground, we can probably go and pull them out because we want to use the duct for something else. But taking these and turning them back into something else is just technically very difficult. I mean, luckily, the glass in them, there's nothing special or dangerous about it. There's no reason the glass can't be reclaimed, and it often is, not all the time, sadly, but you can take them back out of their protective coatings, and you can melt them down and use them for bottles. You couldn't use them for fibres again. The only saving grace is that alongside the development of very high-tech glass fibres, there is development of other fibre technologies, and other things that fibres are made out of. And while none of them are ever going to come close to glass yet, maybe one day, but you know, the most common other research thing is plastics, plant-based plastics. People have made fibres out of things that are biodegradable plastics. Then again, they only conduct light over short distances. I mean, the most kind of ridiculous example I saw was Nottingham University produced a thing where they used spiders to produce silk optical fibres. And they got an optical signal down a piece of spider web, a relatively short length. So here's hoping that eventually we stop having to use the glass ones and we can move to something that's biodegradable, probably not spiders, but there's always people working on things that aren't glass. Maybe we'll get there one day. So.
All right, so just before thanking Matthew again, I just want to announce that the next talk will be on Wednesday, 22nd of January 2020, and it will be supermassive black holes and galaxy evolution from Dr. Caroline Wilford from University of Bath. And now I want to thank you again, Matthew, for this wonderful talk, and wish all of you a Merry Christmas and Happy New Year.